factorization over clicks, and how separation implies independence. And then we said if you take the directed graph, if you want to worry about one deseparation statement, you take the appropriate ancestral graph, minimal ancestral graph of all the variables involved. Then you do moralization. Basically apply one, conclude that deseparation implies independence. What is additionally true is also that the global Markov property in the directed case implies factorization. Meaning, if so let's start. Essentially, if star holds for all these statements in G with respect to P, so star connects G and P. So I take G and look at all deseparation statements there. If I can find conditional independence analogously in the P, then P is globally Markov with respect to G. If that happens, the factorization goes with respect to G. We knew that this is not true, so this is not generally true. Why is that? Well, we gave this example. A, B, C, a bunch of deseparation statements imply some conditional dependency, but it can never be written as a graph satisfying all these conditional dependencies. You have to give up on conditional dependency, some of the conditional, right? So this is what we saw last time. And I did most of the proof, except that the equivalence between the two deseparation statements, I just stated it. It's a combinatorial exercise. Maybe I'll just prove one version. Maybe I'll leave the other to you guys. But anyway, all this is it's a very nice paper to read anyway. It's from 1990. It's from 1916, and I think it's called Independencies of Directed Markov Networks. PDF is not very easily available, but with some effort, it can be obtained. Okay, so then, yes, I mean, I have the PDF. I mean, if that means you just search over Google Scholar in a few ways, someone has it in one of these versions, it is there, and then read the paper. Or you pay Wiley, if you have access to the Wiley Science Library, then it's free. Okay, fine. So let's just start with one. This proof, I mean, I felt bad that I didn't fully finish it. So I might as well just give you a gist of how the proof, at least in one direction, goes, which is probably useful.
So it's like digression, just to sort of get the ball rolling to an open question. So, but it's quite interesting that since you can certify independence, or at least conditional independence, somewhat rather succinct and efficient.
No, we are not certifying independence, but rather we are certifying the structure from independence. Dependencies are the oracles that are available to you. I mean, there's a whole story about how you can implement the oracle.
Yes.
For now, I have not even touched it. That would be another 2-3 lectures if I want to describe the existing methods for conditional dependence testing for continuous variables. But let's say you have an oracle that gives you 1 or 0 answer with some probability.
Yeah.
Then how do you use it to basically refine the structure over the graph?
But like, the way I see, tell me where I'm wrong. Like it's actually the graph structure that's implying the.
Yeah. So it's like a testing process. So if I give you a G and a P,
Yeah.
what you can do is if G is compatible with P in some sense or not is what you can test. That's all this is.
Okay.
Yes. Right. And we'll now see
is like, to do this, it's just the local Markov or the factorization is good. Once you do that, you get this all this huge GFC.
GF, exactly. So that's a good property of directed graphs, which doesn't actually hold for undirected. So that's a key. In fact, for Gaussians, it definitely holds. In fact, something stronger also holds, but let's not worry about that. But the thing is, in general, as long as you have a density function over some base measure, then all three are equivalent. Factorization, that's what I proved last time too. So global Markov property, local Markov property, factorization, all of them. But it's not true for the undirected. It's only in one way. Factorization implies separation, implies independence. That's all you can say. But whether separation implies also whether these things imply factorization, no, that's not true. And the example is actually
this. The interesting thing is that this factorization will be very fast algorithm to test for these systems.
yes,
Almost linear time.
correct. This characterization gives you an algorithm to test what you say. Right now, let me try to prove whichever direction is easier. So what I wanted to prove was beam separation implies separation in the ancestral graph, and then this implied independence. This we did last time, right? Now, if you want to prove this link, let's say I just want to prove only that link, I'll try to prove the converse, which is not separated in the ancestral graph implies not deseparated in the true in G. Not separated in the ancestral graph would mean not deseparated in G.
Moralized.
Yes, the moralized ancestral. Moralization of the ancestral graph, including X union Y union Z. Not separated means not deseparated in G. So the converse, I mean the contrapositive would imply what we want, right? I thought I would just mention this proof a little more detailed. That's all, right? So what are we assuming? So first of all, we are only operating over an ancestral set. The G is already there, implicit, baked in here, because all the nodes I'm including here are from the G's ancestral sets with respect to X, U, and Z. Okay, but the graph is undirected. So what I have is a bunch of variables A, bunch of variables B, and a bunch of variables S, and there's some other variables in between. But all the variables are either in A, B, or S, or ancestors of A, B, or S in my original. So if there's any node hanging outside this set, it should have a descendant in either A, B, or Z. A, B, or S. It's for sure. Okay. Now what am I saying? It is not. I mean, this is not separated. Okay. So what is the hypothesis? X is not separated from Y given Z in the undirected graph.
X is ABS.
Oh, sorry. Let's just do X, Y, Z. Doesn't matter. So set X, Y, and Z, all disjoint sets. And I'm only operating over the ancestral graph. They are not separated. Just not separated, meaning the usual not separation. There's no deseparation here. So they are not separated, which means I can find a path going from X to Y that basically avoids Z. Okay. Just look at this path in the original graph. Suppose this never had a collider, right? Then you already found the path which connects G. Why? Because I have not conditioned on any non-colliders, right? They are avoiding a Z, so there is no problem. So we have taken care of one case. So let's take the path B. So let's take a path B that avoids X to Y or between X and Y, whatever, right? Then suppose P does not have colliders, we are done. Remember the definition of deconnection. If I have a non-collider, I have the condition. So the thing, if I want to block it, If I have connections, then it should not be there in the C set. This satisfies that. It does not have colliders, and all the non-colliders are not in S, so we are done. Okay. So the only problematic thing is you have a vertex, let's say Y, that is colliding. You have a pattern like this in your chain somewhere here. Okay. So two things can happen. If this was colliding, let's say, either so there's a descendant in Z, in which case life is simple again. Why? Because this opens the path in the graph, in the original graph. Right? Because I'm conditioning on the descendant, so it opens the collider path. Right? So we are done if your descendant lies in Z, then you are done. Okay? Now you might say, okay, there is a vertex and it's a collider, but the descendant is not in Z. Then what do you do? Okay, so let's say you take another node. So I don't want to erase this. Let's call it Y prime. Again, same thing. It's not in Z, but its descendant is also not in Z. Okay, then what would you do? Well, if the descendant is not in Z, then what you essentially do is you can find a path over here. Okay, such that it has to be a descendant. So some node in X or Y has to be a descendant of Y, because I'm only looking at the ancestral graph. You said there are no descendants in this set, which means this must have some descendant in X or Y, because only the ancestors are included. It's a minimal set, so we are not including any extraneous variables, right? So this node, if it doesn't have a descendant in Z, it must have a descendant in either X or Y, and it's symmetric. So without loss of generality, descendant only in X. So what happens is you have a path like this. So you break the collider and you create a new path. This has one less collider. Okay. So 4 collides, but no descendant in Z, but an alternate path can be found where this is wiped out. When I say wiped out, what I meant is the path still passes through Y, but there's no collider in it. So I got a new path that still avoids Z, but then it passes through Y. Okay, that's very clear, because it didn't have descendant Z, so the entire path must be in X. Right? Because if Z intersected any one of those, then that would be a descendant of Y. So this path has to completely avoid and then go into either X or Y. But if it did, I can take this path and avoid the collider. Okay. What other complication could arise? Because I'm looking at the moralized graph. So I might be going via edges that are not there in the original graph. That is the fifth condition. So fifth condition is like that, right? So the fifth condition is that you can have an edge that came out of moralization. Okay, no problem. If this happened, it can only happen because there was another Y where it was unshielded and you actually shielded before the operation. So instead of going through this edge, go through this Y. Now you've created a collider for every marriage that you have, or every moralization that you have, which means now it reduces to case 3 and 4. Reduces to case 3 and 4. But we keep doing, yeah.
Y might not belong to that aspect.
But that doesn't matter, right? So if y may not belong to it, doesn't matter. But then you can actually think about whether y is an S, y not an S, and things like that. Because of the moralization, this edge, these nodes are included because of some descendant relationship, essentially, in the ancestral graph. So I already taken the ancestral graph and then only I moralized, right? Which means y was in the ancestral graph. So y cannot have been used. Okay. So your main argument is y not equal to, right? But what I am saying is pick that y in the ancestral graph that led to the moralization.
First you pick the ancestor graph and then you modelize.
Yeah. I mean, it may not be any y, but it is some y. There is one y for which this moralization is justified. You take that y, and then you break this path and you go through this. Now you are reducing to case 3 and 4. Now you go through the same case. Y is an S, y has a descendant in S. Y might be an S itself in this case, but that's okay. That's great. So y is an S or y has a descendant in S. Okay, both are not there. Then you again do the same argument. You can find another descendant in X and you can break the path. So eventually what will happen is you will have a path where either there are no colliders or there are colliders which are in Z already, or its descendant is in Z already. So if you recurse through, you recurse through 1, 2, 3, 4, and 5, you will end up with either 2 with no colliders, avoiding Z, or with colliders, where either itself or its descendant is in G. This implies you found a path that deconnects X and Y. Okay. I only proved this thing because that's all that's required. Because I wanted to only prove deseparation implies independence. I didn't really care about the other way. So I thought it was important to prove this thing. The other way is also true. You can go ahead and they are equivalent actually. But I only proved one direction. Okay.
The moralization aspect is used in the
Yeah, the fact that once you have a hanging Y, it must have necessarily have a descendant in X is because of the ancestry. The other fact is that if you have a moralized edge, it got moralized due to some Y, but that some Y is necessarily was in the ancestral graph. That also is automatically, right? Because of the operation. If flip it, then there is a problem. So all these are crucially used and the proof is there any problem with the proof? Okay. This is in fact one of the most important proofs in all of this causal business, because from here starts all of Pearlian things which we'll go to now. Okay. Yeah, I wanted to only prove this link. So I took the contrapositive. Connection in moralization of ancestral graph implies connection in the deseparation sense in G.
So it's an if and only.
But it's an if and only, but I proved only the direction I needed to prove. But it's a very stronger result. And that you can read from Lauritsen's paper. Right? Because
last lecture we said separation implies independence for these.
Yes. Yes.
What are those undirected?
Yeah, so you basically take only the ancestral graph, the factorization over some, then you look at the factorization, it will imply a factorization over the cliques, essentially. And the cliques are these bunches, Xi and PAI. We basically discussed
What are
that.
those products?
That's just separation.
So the class of distribution should satisfy
Graphical.
Oh, that is called,
graphical models.
yeah, graphical.
models. Now,
They are called globally Markov.
going from independence to separation, they are saying you needed product. W product.
We never went from independence to separation. We only went from this implication to factorization. That required the argument that there is always a sync node, and you do an induction argument over the n-1 variables. You look at the previous lecture I did with that. You look at the induction argument over n-1 variables. Essentially, do a conditional factorization. Then you apply the local Markov property, but the conditional independent version of that because it is implied by deseparation. Then you refactor out. So you will get one factor out for the sync node, and then the rest of them will remain as joint distribution. But inductively, you assume that n-1 also factorizes like that. So it's like you chop off the sync node, nothing changes. So the reverse is not very difficult. So this to that just uses the fact that it's a DAG. That's the more important thing. But undirected graphs, you can't make that statement. Okay, this is complete. Now, once you prove that deseparation implies independence, you might think it only applies.
It's kind of interesting that you get an undirected, like somehow the undirected one seems to lose a lot of information. But I guess the starting point is that they're doing it for a specific experiment.
XYZ, and I'm using the ancestral graph to do it.
Yeah.
So it's not that I'm not losing information.
Yeah.
But when I choose the subset of nodes I want to normalize over, I've already taken care of a lot of things implied by the graph. If the graph ordering were different, which it could be for Markov equivalent network, I will come to that yet. Discovery
This ancestral set would change.
will change, but you still go with that and then. Is that clear?
Completely interesting that like something that's very hard to even think here. Whenever you get a polynomial from starting from a definition that has deseparation by itself is
Complicated.
yeah.
Yeah, it seems like you need to check all paths, but it turns out that this characterization implies polynomial. Now, let's go into the actual Pearlian stuff. So what I told you before was the definition, causal things happen only when you consider P star, which is the set of all interventions. So all we have proved so far is if we take one distribution and if some G was Markov with respect to that, like in terms of factorization or locally Markov property or globally Markov property, all of them are equivalent. That's all we have done, right? So we've completed the equivalence between conditional independent signatures and independencies found within one distribution. Okay, but what makes causality work is invariances across distributions. So we need a way graphically to capture that. Otherwise, we can't actually say that some interventional distribution can be estimated from observational data. Because there's some imaginary distribution you don't even see, even if you assume it's a causal Bayesian network, but then you need to estimate it from only observational data. So it's not very clear how do you do that, right? So we will derive three rules. They are called the do calculus rules. The most canonical way it is stated is a bit complicated. I will state it. Okay, someone says, could you keep the camera zoomed out so that we can see the entire board? Actually, now I've erased everything in the board. So yeah, let's now go to do calculus rules. But before I go to do calculus rules, I have to introduce the most important thing, which is a structural causal model. So far, I've told you a story about causal Bayesian networks. I haven't told you anything about structural causal models. So let me actually go to structural causal. Because the notion of identifiability is usually defined with respect to structural causal models. Okay, so you just need to know what it is. Okay, so structural causal models is actually a bunch of things. So the most important thing is a bunch of functions. We'll denote it as M. Okay, short for causal mechanisms. A bunch of causal mechanisms, right? Then the superset B, which is a bunch of observed variables, and a bunch of unobserved variables, exogenous variables. They are always canonically taken to be independent, not identical, but independent. And then there is a G, which is a DAG.
M again?
I have to tell you what it is. So for all I, xi is nothing but a function of xpai, comma ui. Okay, and all these. Okay, so let's call it fi because a function depends on the node. Like for every node, there is a function that generates the data, and these functions, including all their arguments and all that, is essentially M, the mod. Okay. So when I say a structural causal model, I mean M, and there are a bunch of exogenous variables. So by the way, P of U1 till U K, there need not be, by the way, there need not be equal number of exogenous variables as B. There can be some smaller number. It's just that multiple equations can depend on the same set of exogenous variables. But what matters is how many ever they are independent. Here, some implicit right-hand path principle is used. Because if they were dependent, you could always consider some slightly more involved model where you can keep going until you find all the common causes, and they must be independent. So that's the intuition behind stating the canonical form of this particular. But it loses no generality. Yes. Yes. No, so B. Unfortunately, my notation so far has been this. I apologize.
Like definition would, for example,
Imply, yeah, correct. So an immediate implication is that this actually implies. Okay, so I have to tell you what do intervention means.
this will correspond to a causal link.
Yeah, it corresponds to a causal Karthikeyan network with respect to V. Now, question is I have to tell you what theta is in this sense. So when you said do X, so when you do, I only have to tell you what happens when you said do Xi is equal to H, right? So this also I have to mention. So this only then the definition of structural causal models is complete. Equations don't mean anything. What it means is that when you said do Xi is equal to I, X, you basically replace X is equal to X. You delete this equation. All other equations will remain, but only for Xi. So only for I. I've just told you the definition for an atomic intervention, meaning one node intervention. But even if there's a subset, you go to all those I's, you just simply replace by those values from the interventional distribution. So, for example, if you have a graph, 1, let's say 2, 3, and 4. Let's say I do x2, x3 is equal to small x2, x3. Then what will happen is x1 is x1 always. X1 is u1, and x2 is equal to small x2. X3 is equal to small x3. X4 will retain its function. F4 of x3, x2, u4, whatever that is. Yes.
Why are we assuming single independent variable for dependent?
What single is it?
So your notation says xi is fi of x parents of I and ui.
Yeah, so actually, very simply, ui belongs to u, but we are not saying that for different I, the uis are different. We are not saying.
So one ui cannot cannot be the cause of two excess.
It can be. It's okay. That's my definition. I mean, generally it is stated with independent ones, but we will state the more general one. Actually, this is called semi-Markovian model, where the exogenous variables are allowed to affect multiple things, and they have no parents. Yes.
That execution is one direction that you have an SMBM that implies.
Okay. So we have to be careful there. Yeah, you're right. I know what you're going to point out. So if UIs are distinct, P star is CBN with respect to yeah. Okay. Otherwise, it's a semi-Markovian model, and we'll come to semi-Markovian.
The P star is how you obtain this.
Yes. How to obtain P star?
Will again correspond to that truncated.
Yes, and that's a claim. You can check that. Yes.
If I have a C star and G, can I say that there exists an FI such that?
That is the problem. I don't know the answer to. I have no idea.
They at least for good models like Bernoulli or.
So you should realize, right? You are see from here to there, it's only mathematics. But from here to here, it's physics. You're telling me that there is a real world phenomenon, there is a real world set of functions that actually compute some bunch of variables and actually give you xi observability. It's not a computational. I mean, I can always produce something with some f's that I manufacture in my computer. But what you're saying is it's always produced by a mechanism, a causal mechanism, physical causal mechanism. So you're making an epistemic statement when you go from here to here. I have no idea about that. Maybe you want this, you want to imagine a world where that's true? Yeah, sure, you can. In fact, classical physics does imagine a world. For all the statistical distribution of gas particle velocities and pressure, I mean, all those classical things that you read out of Boltzmann, they do assume that there was a functional equation connecting all these particles. That is true. But whether that thing is true post-quantum, I don't know. And the other question is, can you get a CBN? Like, can I just keep intervening, keep measuring distributions, and I just have to check all the conditional dependencies? Maybe it is Markov with respect to some specific G. But there is no classical function that actually produce X. I don't know. I'm not saying anything about it because I just don't.
Why are you saying this reverse resistance?
Because when I mean this, I actually mean there has to be a physical function that actually produces it. This is an actual measurement in the real world. When you mean, I mean, that's what I meant. Okay. So if this is actual data from the real world, and let's say you have access to infinite amount of data, is it always the case it was produced by some functional mechanism, classical function? I don't know. Yeah.
This is the realizability aspect.
Okay, so since you asked all these questions, I will say there is a very beautiful paper called, so I don't know the title of the paper, but it's a very recent paper by Shalkov, 2000, and others, a lot of other people, Shalkov is part of it. It's called Extending Definities Theorem, or it's called Causal Definities Theorem. It doesn't answer your question still, but it does say something about if an observational distribution or some interventional versions put together, if they satisfy some more general version of exchangeability, it must be explained by some causal relation. Invariances will be there. Okay, you can show that. It's ab initio. Meaning, I'm not telling you anything about some model story. It's not an. So this is like a model that I'm giving you and I'm showing you implications. You're asking the reverse question. In the real world, if I ever see a P star which is a CBN with respect to G, can I assume that there will always be a structural causal model? I don't know the answer to that question. But what is known is that a slightly weaker version, if I just observe some bunch of distributions satisfying some exchangeability properties, a more general version of it, then it turns out that there is a CBN that fits some. You can show that. Because a lot of people always question, why do you start from this? So, I mean, why do I have to care about your model? What we are saying is that as long as you have some exchangeability properties in your data, and they give a very beautiful healthcare example, like you never treat some different patients differently or something like that. Once that is true in a hospital, then it immediately implies that there is a CPM. May not know it, that's okay, but there has to be a CPM. That they show. I am not so sure about this functional relationship. That is a bit epistemic. I mean, nobody knows. I mean, if you can prove it, I would like to know what you assume to prove this. But it would be very, I mean, it would be very surprising for physics people, because physics used to work under the assumption that there was this work. But now we know we have observations which don't correspond to this work. So I am not so sure if you can prove this.
I think if the values are discrete, I think I basically need a mapping from a random variable to some other random variable.
No, I think you are treating this very lightly. I'll tell you why. If P star is a CPM with respect to G, all interventional distributions are fixed, but counterfactuals are not. But when your SCM is fixed, counterfactuals are fixed. Now you are telling me by fixing just interventional distributions, there is always some functional thing. So you see, right, there's a non-unique mapping already. There have to be a bit careful about saying, oh, there's this unique F that's it's not unique for sure, that we know that. You are just saying, okay, there's at least one function that's satisfied, perhaps. Okay. Then, so this is very clear, right? So BOI are distinct P star CPM with respect to G. I just have to tell you about what happens when there are U's that are shared between multiple variables. Okay. Now that's called a semi-Markov model. What that would look like? Actually, there's a more complicated treatment. I'm just simplifying it. You might ask why even semi-Markovian model is a correct thing to look at, because you might say, okay, I'll have a bunch of equations using some UIs, and then I observe some subset of them, right? And that's the more general model that you can have, sure. But there is some reduction to this canonical form in some sense. But I will just go with this treatment because much simpler.
So that is a semi-Markov. This is Markov.
No. If UIs are distinct, this is Markov. If UIs are not distinct, then it is semi-Markov. I'm going to talk about semi-Markov. So let's take the simplest example. So you have 1 and 2, and there is one common U that actually causes both 1 and 2. Okay, maybe you should take 3 also. Right? So in this particular case, from the viewpoint of deseparation, that is conditional independencies, you can only condition on what you observe. You cannot condition on what you do not observe. Okay. And in this model, U never has a parent. Right? U never has a parent. It's always a U never has a parent, but it's a common parent of many. It could only be a common parent of many. So it cannot be a collider at all. Right? So when you leave something, when you go to U, you can always travel to anything you want. Always. The only problem can happen only at the observational data. Maybe when there is a collider, depending on whether it's conditioned or not, this can get blocked. Okay. If you think about it more carefully, it doesn't matter if I have one latent like this or this one. So when I mean double arrow, I mean there is one U12, U23, and U1. Okay. My claim is that for every model of this form, I can always find another model with some exogenous distribution such that nothing in my thing would change. I mean, I'm making a very intuitive argument, but I'm only making an argument with respect to deseparation for now. But there's a more elaborate argument that says that if you actually have a latent model, in the sense that there are a whole bunch of variables, but you observe only a subset of them, and if you can always find some equivalent functions of this form such that the interventional distribution will match. It's a very complex statement, but it's true. Okay, and there's a theorem by Verma and Pearl also. But from a deseparation point of view, which is what I'll be using throughout, and as far as this P star is concerned, which is calculating in whatever interventional effects which I'm going to use deseparation all the time. Observe that deseparation cannot change between these two. Why? Because if I enter 1 and then I can go to 2, and then I can actually go to 3, or I can go to some other variable. But all that would actually can be carried out here because all pairwise relationships are taken. Right? Because if I want to go to 2, I can go to 2. If I want to go to 3, I can go to 3 through this variable, and that's all that matters. And if there was any conditioning, it will happen at the observational level. If it creates a collider, here also it will create a collider. If it doesn't create a collider, here it won't create a collider. It's very easy to check. Just a small observation, but that's true. Okay. So if we have semi-Markovian model of this kind, without loss of generality, you can only assume that it affects 2 children, not more than, and it doesn't affect anything. Yes.
Following the equivalence between these two, because in the first statement, given U1 and 2 are independent, or any of them, here it's always dependent.
Yeah, okay, given U12, U23, and U13, all of them are independent. I mean, what are U's, right? I mean, it's unobserved. I mean, you will never get to see them anyway. So what is the point of saying conditional independent statements that involve U?
I see. So there are 3 other variables between 1 to 3 which are observed.
There's no observation here. These are also not observed. But I'm saying it's equivalent model. From a perspective of working only with what you observe, and any deseparation statement is valid here and here. There's no distinction. What?
How you have cycles in this?
No, this is that.
Put like a new vertex, you want to connect that.
No, there are undirected cycles, sure. There's no directed.
How are you doing that bidirectional?
If you want to connect it to the
U12 is a vertex connected to 1.
Oh, I see. So you are checking it.
Okay, so bidirected edge means.
So you are just saying this hidden variable will affect at most 2 nodes.
Yeah.
Okay. Without loss of generality, you can assume that they are done.
It's a very minor point. But there's a more general version of in Verma and Pearl, 1990. That even if you had parents and that was observed and so on, there is an equivalence to this model. That's not obvious, but that you can take.
And if they are equivalent, then what is the issue?
There's no issue. Just that I can always consider UI to have 2 children at most. That's all I'm saying.
So in the second one, they have to.
Yes, this is equivalent to that. What I'm saying. I mean, there's a more combinatorial way of saying for discrete random variables. If you have 1, 2, and 3, and let's say its alphabet size is 2, for example, there are 8 possibilities. Your U cannot be arbitrarily complicated. It has to only tessellate the event space into 8 and no more, essentially, right? And that's why you can actually divide this into, and if you do the tessellation appropriately, you can actually create pairwise variables. That's all it is saying. It's not saying anything very more complicated. There's always a tessellation in such a way that you can isolate the component that confounds 1 and 2 and isolate another component that confounds 2 and 3, and there's another component that confounds 1 and 2.
So when you say those 2 models are equivalent, you mean that the deseparation statements in both
CDN, distribution, yes.
the observed distribution,
Yes.
the CDN, everything.
Equivalent. I am not claiming anything about this. Right?
But we demand that U's are independent. In this case,
Even here U is independent. These 3 U's are independent. Yes, I do demand that.
but in this case, you want to like the conversion from the first case to second case, you would have U12 is equal to U23.
Yes, it's
And
fine.
therefore not.
Oh, and then let's say when U is coming, 1 is equal to 2 is equal to 3 is equal to U1.
1 is equal to.
1 is equal to U2 is equal to U and 3 is equal to U.
Okay, so you're saying U12, U23, and U13 are not independent.
Yeah, how would you? That's
1 is equal to 2 is equal to 3. is equal to U. That's your point. Right?
Yeah, all the equations are of that.
Yeah, that will create a problem. Okay, so that conditional dependency will create a problem.
You can create a function from like you want to indicate
You write indicator that yeah, U12 is equal to x1 comma x2 or something indicator. I mean, I think you can. I mean, all I'm saying is it's a product form, right? So, but you're saying that it's but it's a constant. You want it to be equal. I don't understand what you're. Okay, so you have a common distribution that varies, and you said everything else equal to.
Will not be.
There should be a way to do it, but
sometimes you force, like you want to be identically distributed as U, and then 2 and 3 are equal.
Yeah, you can impose equality in the functions. You can do all of that. But what you are saying is that they're all changing together and they're falling together. Right?
like in the observation, you see like 1, 1, 1, 2, 2, 2, something like same value.
No, but D separation will not change. That's very
Right,
clear.
but, say the distribution will also.
The P star will not change. I claim that there is another P star that will be equivalent to this. And what you are claiming is that it will not be. Even P's. So my only problem is if the interventional distribution, what will actually happen? So if they intervene on two, it is a pairwise one, which can be explained by this. If I intervene on the other one, it's the other pair and can be explained. So I'm trying to see. I don't know how to describe the joint distribution P star, but what I do know is that there is a result of this one.
Maybe it is restricted to those bases.
No. So the way it works is, okay, not P star, only P. The observational distribution alone you can actually match. That's all I want to say.
Even that I don't see.
Even there that you don't see, but there is a theorem that says that if you actually have a latent model, meaning there are many variables, but you only observe over a subset, and it's generated by some set of functions, it can always be generated by another set of functions where the U's are actually pairwise and the distribution is faithful. Oh, you are creating a distribution that is not faithful.
Yeah.
But yeah, so it is not faithful. So okay, faithfulness. Okay, Verma and Pearl requires two things. Okay, I forgot about that. So latent models permit pairwise independent latent. That's effectively what the theorem says. Under faithfulness.
How did it violate faithfulness?
Because faithfulness would imply that no, it is faithful to the true latent, the full model basically. But if you set the 1 is equal to 2 is equal to 3, no matter what, they are dependent. I mean, constants, right? So they are dependent. No, so for example, conditioned on 2, 1 and 3 should be dependent. But in your case, conditioned on 2, everything becomes a constant. And therefore it's independent. So you are violating faithfulness. So it seems like, yeah, you are right. So it's not hold for P star, I apologize. It holds only for P. And there's a theorem in Verma and Pearl 1993. Since I made the mistake, it is in the causality book. However, D-separation statements still hold, and I'm not going to use anything other than D-separation when I actually go to CPNs. Sorry, the interventional distributions.
So for D-separation to hold, you don't need faithfulness.
Yes, for D-separation to hold, I don't need faithfulness. So any conclusion I make only from D-separation statements, this would hold. So it's enough to consider a semi-marker. That's all. Yes. I mean, the theorem says that if there was a latent model, only on observational data it permits pairwise independent latents under faithfulness. That's all it says. here he gave a counter example where u is equal to, let's say, u is like probability Bernoulli half, right? And he just simply set all 1, 2, 3 to u, right? And it made all of them dependent. But I claim that you can actually make it into 3 independent u's. But if that were to be true, there's a problem over here. So the thing is conditioned on 2, 1 and 3 are dependent still. But if you set everything to be the same number, conditioned on 2, 1 and 3 are determined. Right. So it's a faithfulness violation. So at least this can't be true for that model for sure.
With condition on 2, here also 1 and 3 are different.
Yeah, but here it's independent. Because 1 equals 2 equals 3. So when you condition on 2, there's no entropy in either 1 and 3. So 1 is a constant, the other is a constant. I mean, it depends on what's your definition of mutual information between 2 constants. I mean, I consider it to be 0. So this is in Verma and Pearl 1993, and it's in the Causality book. You can read it. But the whole point of saying all of that is that for without laws of generality, I'm going to assume that U's have only 2 children. That's all I want. But it's okay to have multiple children. Nothing I say will change, so it doesn't matter. But I just wanted to make a remark because a lot of people assume this to prove things. Yes.
Sorry for the basic question. So faithfulness is characterized by this, or
No. All I'm saying is this translation can allow like the same distribution to be explained by another distribution from this class only under faithfulness. That's all.
and what is faithfulness?
Faithfulness means all independencies must be explained by the structure of this graph, of the whole graph. So there are complications that come when you observe a subset of them, and there are other latent. So that to be very clear. Okay, but the side track is just to show that I can just generally consider UI to have only 2 children. But if you're comfortable with it, multiple children is also fine. The only thing is I want you to be able to read deseparation statements even over this. All I'm saying is whenever I represent something, I represent like this, but it doesn't lose any generality in what I'm going to say. Okay, so these are semi-Markov models. Now let's come to the thing that I've been trying to come to for almost 8 lectures, to calculus. Okay, let's go back to the beginning. We started with ignorability, and we asked the question, when is ignorability even true? So the question you might ask is, if I have a G and P star is a CBN with respect to G, I don't see all interventional distributions. By the way, I only see P with respect to some model M, and then it's a CBN with respect to G. I know only this. Okay, but I gave you already that P star, which is obtained by surgery on M. And G is a CBN that connects all of them. I've already told you this. So I've given you a lot of information, but I only observe this distribution. I don't observe any other distribution. Now I ask you, what is the probability of, so this is a scalar, given Y, this is a vector, do T. I intervened on a subset T. What is this? This is what I'm asking. Okay, this is nothing but Pt of X given Y, my previous notation. Usually you set it to a constant, so I'll just set it to a constant. This is what I'm asking. So clearly, you told me P star is obtained by a surgery on M, and you gave me the graph. I'm asking you this interventional distribution, right? So you might say you already know all the factors, so maybe you can actually figure out this, right? Sure, you can if UI are distinct. Because only then will be a CBN with respect to G. I never said anything about the semi-Markovian. Now, when you consider the late, if somebody actually gave you all the latents such that this property would be true, then you can again replace and then figure out what P of P, T of P, X given Y would be. Because I gave you G, I gave you P, you know how it factorizes, therefore you can write down the equation. But in semi-Markovian models, when there are latents that affect two variables, you can't actually write it. I mean, you got it. Truncated factorization is not true. Not true in semi-Markovian model. I mean, but another factorization is true. I'll just write it. It's just for so it's just product over again P of xi given P of I, comma ui. By the way, this can be deterministic function, so it's not a problem. Multiplied by all the u's, the joint distribution over all the u's, and then you sum over u's outside. So this is the observational distribution. Okay, let me not confuse you. Let's call it P of. Okay. Now, when you intervene, the truncation will act here, and it will leave everything else the same. Okay. So you will still have the summation u, and you will have I belonging to I does not belong to T. P of xi given x P of I, comma ui, but only the factors that matter, Pu, and the indicator that the intervention T must be consistent with V, with XV. Okay. XV, the joint. I'll change the notation, sorry. Okay, so what has happened? If UIs were distinct, I could use the truncated factorization and solve all your intervention points and have a problem with that. But if the U's were not distinct, right, then at least it has more than one children for some U, then this is the factorization that it will have, right? Because there's some graph for which there is a bunch of latents and so on. So if you take this structural causal model, it will imply this particular. But there's a summation over U. So there's a product over the rest of the things. This complicates matters. So this is not a product form anymore. So the truncation has to be applied before the average. Okay. This creates a problem. Because you don't observe this. But if you observe the full product marginalized, it does not imply you know anything about the partial products marginalized. That is where the identifiability issue comes in the first place. Okay, so at least in general, it appears that if I just ask you the interventional distribution, and if U was coming from a semi-Markovian model, you can't estimate this from just this, right? But the first interesting answer is that depending on the T and the G and X and Y that you ask the question, I can actually give you a formula that depends only on the observation. Okay, that is the ID problem, but we'll formally state it.
One way to view this is that there are these unobserved parents UIs that you can have. So you have to somehow.
The gene, that's exactly Fisher's example. It was an imaginary gene that caused you to smoke and it gave you lung cancer. What can you do? You can only intervene on smoke. But can you intervene on smoking? You can't. So you have to do something else to determine. But I can't say anything from the correlation.
So you could, if it was P of U was just product of P of Y.
No, it is. That's
in the
fine.
Markovian.
That's okay.
Then you can estimate international distribution from
Not necessarily. P of U is unknown, right?
Look at the left hand side. U is in some sense marginalized away from the left hand side.
Exactly.
That's why you are coming at us, and that's causing you. Like some makes things funky. I mean, because you have to marginalize it. The left hand side is not X. X V comma U. This is.
right.
Okay. So M.
From observation, you cannot estimate international distribution.
Yeah.
When in any set of books. Karthikeyan or Karthikeyan.
And at least to me, and maybe Karthikeyan correct me, the way I'm seeing it, I'm giving you marginalized random movable.
Correct.
Some other ones is I didn't even show you, and I'm only giving you marginalized. There's no way for you to reconstruct the
In general.
go back to the unmarginalized.
So we'll formally state the problem. Okay. So M is a semi-Markovian model by which I mean an SCM. Okay. And if I change, okay, so a semi-Markovian model, and it also factorizes. When I say CBN, I mean this version now. Okay, it's a general version, but this version. Okay, it doesn't matter. So it's a CBN or let's say a generalized CBN. I mean, there's no thing called generalized CBN, it's just a CBN. CBN with respect to G. Okay, so I've defined all my interventional distributions with respect to G implicitly. I don't know what they are. All I have is PM of B, PM of X. Let me just define some notation. When you intervene on T, we will call it an intervention on PM of this, right? So so the problem is there's already a subscript, and I need an interventional subscript. So what I do is I'm going to do subscript or subscript. Okay, that's the only thing. So I'm going to call it MT, which means I take the model, I take those equations in T, cut it off, set it to T. That's it. Okay. Times X. This will basically form P star. And it's this generalized CPM with respect to G. That means it obeys the truncated factorization. That's all I know.
MT is just what you are earlier calling. What's the difference between PT and T?
Okay, MT is a more descriptive thing, which is you take the SCM equations, you replace that, and you generate the distribution. Yes, that will definitely have this. I'm not making any distinction, but counterfactual may mean other things. That's why I'm making a clear distinction. I'm only defining it through an intervention on the SCM. Okay. Okay. What is the ID problem? Which goes at the heart of Simpson's paradox. ID problem is the following. If you can find M1, M2, that is two models, right? Such that PM, by the way, M1, M2 gives rise to the same CBN G. So graphically, they are the same. The functions might be different, the use might be different. Okay, but I have two models, but they are all a CBN with respect to G. And what am I given? Only observational data. And it's just one unique one. So there may be two models that actually coincide on the observational data. So this is coinciding on observational. So this already has fixed all truncated factorizations. Combinatorial. Like all these are fixed. I just don't know the details. But whatever they are, the observational distribution is identical. That's all I've said. Okay, there could be many such models. And the beautiful question here is P is equal to T of X given Y. When is it unique? If it's unique, it's called identifiable. People use the word ID. If it's not unique, it's not identifiable. Which means observational data is not enough. Even if you give me the graph, it's not enough, essentially.
Now, how are you defining PP of P there? You have to do it with respect to a model, right?
So I can always this is the okay. You want
So there were two M1, M2.
yeah, with both I mean that's why I'm asking when is it unique. So this is basically P MT of X given Y. Precisely, there are multiple M1s and M2s. So potentially this can be different. So I'm asking you, when is it unique? They are not always, I mean, they are sometimes they are unique, sometimes they are not unique. So we are going to find out the cases when they're unique. In fact, this problem was fully solved for exactly this setup under semi-Markovian model, U with no parents, multiple children, by Spitzer. Pearl in 2006. Okay, the short answer to the question is that I'm going to give you a bunch of rules that allows you to go between interventional distributions and observational distributions. If you can find one sequence of production rules, if you call it production rules, because you guys are familiar with all regular grammars and all that. So there are three rules I'm going to say. They can be recursively applied to any set of interventional distributions. Now, if I start with my query and I follow that production rule, and then I land up only with quantities that has observational things on the right hand side, then it is identified if and only if. Okay, and the three rules I'm going to say. So the problem was that it was actually the three rules were proposed in 93, 95. For almost 10 years, we only had sufficient conditions. If this is the G, if this is the X, this is the Y, then it's unique. If this is the G, this is the X, this is the Y, then it's unique. And there are many, many conditions, two of which is backdoor adjustment and front door adjustment, which I'll cover today. But there is a more general characterization, which is if the so there are three rules. I haven't told you what the three rules are. I'll come to the three rules. If those three rules cannot lead you to an estimate where you only have observational distributions on the right hand side, then it's not identified. Okay, and they had a more combinatorial way of identifying this also. We'll come to that. But I only want you to understand what the problem is. The problem is there are multiple SEMs that are CBN with respect to the same G. So it will have the same truncated factorization. But we just don't know what the details here, P's are and the U's are. Okay. But all we know is that observationally they are equivalent. And then we are asking to a different interventional distribution. So I'm replacing some equations in my SEM by some constants. So it gives rise to new distributions. Right? Clearly, if the models are different, you would like to say that these are different. Sure, they are in general different. But the question is, when is it? And this is the answer to the Simpson's paradox in the Pearlian frame. It's a very specific answer, but yes, yeah.
Sorry, when you say when is it unique, you mean when can I find some t equal to t such that separates?
No. I give you a t, I give you an x, I give you a y. This is a query, and there's a g. For what g and pairs of queries x, y, and t is it unique?
Is what unique?
Is the interventional distribution unique? Is this unique? That's what I'm asking. Like, see, this has lost information, right? Like as he said, so you need to create new information. The question I'm asking: do you need to create new information in every single case, or can G actually help you make some things unique? That's the question. Yeah.
So you mean NP can NP be found uniquely?
What NP?
T NP of x given. Because
Yes. Can be found uniquely, no matter what M is, as long as it matches the observational distribution.
Think of it as non-unique. Like I give you X, Y, and T. You then give me two M1 and M2, two different models. They completely agree on your observed data. Everything you observe matches, but the interventional distributions are. So they look like the same models. But once you open them up, one is an alien and the other is a.
So observationally, certain models can align, but interventionally they may not. So you are giving me more so you can have a more general thing. So I give you PM1, M2, then PM1 of T for T1, T2, T3. So I give you a bunch of interventional distributions. You can ask this question again, when is it ID? All this has been solved, actually. Okay, but the canonical thing is only observational data is known, then what can you say about that? That's exactly simple. Yes.
The graph is also.
The graph is known, yes, very important. If you don't know G, there's nothing you can. My claim here is that even if you knew G, there's nothing you could do because of the marginalization. That's the key problem. Okay. If UI distinct is done, right? You guys agree? Yes.
So for some pair, so you said there's a tuple x, y, and t given to you. For some t's, it might not be identifiable.
Yes.
For some other t's, it
It
might
might
be.
be.
So you take the set of all such t's and then ask for identifiability.
No. The query is for every. The uniqueness question is for every patch,
x, y,
each x, y, t, and g. Of course, if the answer was not unique for almost every g and every t and x and y, then there's no point doing this theory. The fact is that there's a non-trivial answer. That's the only thing.
And it only is defined identifiability is only defined after SCM is used. It is not defined for.
It's not known. We are assuming there's a generative model. That's all. The ID problem makes sense only with respect to M1 and M2 that can explain the same observational distribution.
Without M1, without the existence of M1 and M2 generative model.
The problem cannot be.
So what is the input to the problem? G, M1, M2.
No, there's no M1, M2. Okay, input to the problem. Just G, P of XV, and X, Y, and T. Okay, so this is part of the query. G and P are the only things that are given. So only main assumption is G. P is the distribution. Yes.
In M and G, the U's are also marked.
Yeah, if you knew M, yes, but the input is not that.
Right.
So we are assuming the P comes from some M, but I don't know what M. Yes.
And that M needs to be from some class, or you don't even need that.
I said, because for the definition I need.
Yeah, but is input M also is input? Or
No, it's not an input. But the distribution must have been obtained from one such SCM. I don't need to know what it is. I don't need to know the functions. I don't need to know the parent, nothing.
And you don't need any assumption on what kind of this function.
Yes. No assumptions. No faithfulness, by the way, here. Nothing will trouble you. The only thing I've already assumed is that U's have no parents. Like the exogenous variables have no parents. So it's a semi-Markovian model. And it is a CPM, generalized CPM, like the structured factorization with respect to some G. I've assumed all of that. But that's it. And then I gave you that G and the observational distribution. I don't tell you anything about it. I don't need basically. And the question is whether it's unique or not. If it's unique, you are going to say it's unique. If it's not unique, you are going to say, okay, there could be two M's for which the interventional answer could be different. And there's nothing you can do about it. Yes.
But like non-uniqueness is easier to certify with. I can just give you easier.
Yeah.
So I can give you this M1 and M2. Those marginalized distribution satisfied, but for conditional, those first set of equalities hold for the same for M1 and M2. The second one breaks for VT.
Exactly. In fact, the proof also goes that way. There's a combinatorial condition. If it's satisfied, I mean, it's a big algorithm. If the algorithm ends nicely, then it's ID. If the algorithm says not ID, then I can give you two M1s and M2 such that the interventional distribution will be. That's what they prove. But the second part of the proof is very hard. I'll probably not go into this lecture for sure, but I'll give you sufficient conditions when it is actually unique. That already is very interesting. Yes.
The fact that you can calculate or interventional distribution from the observational, that I understand, that ensures that my PFT is used. But is the reverse true that like if this condition is satisfied, then I can
No, I'm saying that it is not unique in the semi-Markovian model.
But
if you marginalize with respect to U, there's a problem. This given data from here and even knowing G, you can't do anything here in general.
so like it can happen that my there is a unique model, but still I cannot calculate the intervention.
Then you may not know enough about G.
If I know G and I know it's SLBS and I know that it is unique, I can always calculate.
Yes. Because the property only of actually you will find that the P is only there to just estimate. The main thing is like G, X, Y, and P. The answer depends only on G, X, Y, and P. G input may be P. Yeah.
So if your Markov has no UI, no hidden variables, then it is unit.
When you say no, there's always hidden variable. The only thing is that you should not have a semi-Markovian model. You should have a fully Markovian.
Fully Markov, then it is unit.
Then it is always unique.
And if these UIs are like only have single children, then also it is unit.
That is Markovian.
That is totally. Semi-Markov means it can have more than.
More than. You are marginalized. That's it, right? Okay. So now let's go to front door. Before I go to front door, I advertise so much about do calculus rules, so we'll see the do calculus rules. Very interestingly, so I've created too many distributions over here, too many models. There's so many things that can go non-unique. But very interestingly, all that can be like understood from the viewpoint of deseparation. Okay, and that's the main insight in this Pearlian theory, at least the way traditionally it has been. Okay, just one theorem, very simple one. If M is Markov model, UIs are distinct, it's a product measure, it's always unique. Just a simple truncated factorization would solve the problem. Okay, this is an obvious thing, right? Question is semi-Markovian model. Is there a problem?
You have cell phone choice.
I have it here.
Okay.
I don't have it close.
Maybe the box is
Maybe next to this. So
What?
next to the speaker. So you keep it far away.
Oh, okay.
Hey, it's okay.
There's some feedback. But can you hear me?
We can, but maybe the.
They can't, right?
video
So it's not on.
It is going now.
It is on. It is on. Okay. So do calculus rules. The very famous paper by Pearl in 1995. There is one complicated way of stating it. Which I personally don't prefer, so I have to force you to prefer my preference. So I state it through a very simple augmented graph and deseparation. It's very easy to remember, at least for me. And I've used this thing many, many times. So instead of the complicated thing, is a much simpler way, I think. But I need to introduce what is called an augmented graph. But before that, what are the do calculus? They try to actually relate interventional distribution to another interventional distribution or some conditional distribution within the same distribution. So it basically goes across. So you take all conditionals and it's trying to find out when one condition is the same as the other condition. It could be in the same P or it could be some other P. Okay. So the simplest rule is you fix the interventional distribution and you say that these two conditional distributions are equivalent if X and Y are deseparated given Z in G T bar. I'll tell you what G T bar is. So you are taking an interventional distribution. it basically means it cuts off all incoming arrows. At least that much is very clear. Okay. Whatever graph that you have, whatever Markov model that you have with bidirected edges. So general Markov model are always, like for example, this is a Markovian, this is a semi-Markovian model. So you can have bidirected edges like this, you can have bidirected edges in this way. It just simply means there's some latent that's common between A and B, some latent which is common between B and C. I need to specify at least where the latents are. Okay, that's when the semi-Markovian model is true. So this is my graph. It looks like this. You can do deseparation statements even with respect to this stuff. You just have to assume that there's an imaginary U there and you're not conditioning it. That's all I'm saying. Okay. Now, what is GT bar? Let's say this was T and this was X and this was Y. GT bar is remove all incoming edges to T. It just simulates an intervention graphically. Okay, and in the remaining graph, if X and Y are deseparated given C, okay, then this is true. See, all this is saying is in that graph, deseparation is there, therefore it implies conditional identity. It doesn't need a proof. All you need to do is go to the truncated factorization. That is a CBN with respect to this modified graph. So all you have to assume is that PT is Markov or whatever, semi-Markov with respect to GT bar. Okay, this is the only thing you need to convince yourself. Once you have this, deseparation actually implies this. There is no complication. Okay, this is the easiest rule. The next rule.
It's kind of like natural, right? You're intervening on T just means like you're looking at the graph or
yeah,
the incoming edges are removed.
But on both sides there is interventional distribution, so it's very nice. But the problem happens when there is an interventional distribution on one side which is different from the interventional distribution on the other side. That's when things get very interesting. Okay, so before I go there, I need to explain to you how to read off such statements graphically. Turns out that just the graph alone is not enough. So we have just introduced one surgery, which is GT bar. So if I state the usual way it is stated, I need to introduce more and more notation, which is more complicated. So I'll go through an alternate route, which is used by Pearl in his proof in 1995, and it's a much simpler way. And since you know deseparation implies conditional independence, it will immediately you can see the rule being satisfied. So the way to think about interventions, it's a very simple graphical device, but it's extraordinarily powerful. Okay, it's almost used in many papers on interventional design, causal discovery from interventional data, or even reasoning about do calculus with respect to multiple interventional distributions. Name it, and you take almost anything involving interventional distributions. This is a very strong and a very simple augmentation. So here is the thing. You take your graph that is semi-Markovian, which means it has edges and bidirected. Okay. Now you intervene on T. So this is my T. I'm considering PT. So I would like some graph structure that would explain sort of multiple invariances involving T and some other distributions, if it's possible. I don't know if it's possible. I'm just trying to figure out if it's possible, right? By the way, this G itself could be obtained after the surgery on some other like set of nodes. I'm not like including that here. So now what you do is that you just create a new node FT and put an arrow into this. Okay. Now you create a new SCM. SCM is the following. FT has two states. I mean, usually they're called idle and the interventional state, or basically some binary encoding of this. Okay, it's a binary variable. Okay, so if you have the same amount of interventional data and observational data, this variable will have probability half. Okay, so now what I'm going to do is I'm going to take PT and P, the observational distribution and the interventional distribution, I mean, when I say observational intervention, it's with respect to G. It may already have been intervened because you removed something. Okay, so it's a meta thing that I'm doing. So I take a bunch of, I take a graph and a distribution that's marked out with respect to this, and I'm intervening, right, at T. I'm creating a new distribution. Now, what I want to do is, I want to put all these samples together and have one CPM or one SCM. How will I do that? The intervention has been made in T, right? So what you do is very simple. You write for all I in T, you write Xi as f of this is f prime of I of xpa of I, comma ui is ft. There. This is a modification you are making only for this intervention. Now, what happens is, if ft is idle, then it's the usual equation. Now, if ft is interventional, it is just t. It's just xi is equal to whatever that. Okay, so I messed up the notation.
Small t.
Yeah, small t. Okay. So I can create a new SCM. At least with respect to the observational data and this data, you agree that it will satisfy this. That's all I care about. Right? And it matches everything in the observational data. That's all that matters. So if you give me an SCM, I can actually create a new SCM. With all that I'm saying is, if I flip this, I take one distribution. If I flip the other, I take another distribution. But the key point is this total thing is a CPM. Okay. And I'll call it an augmented graph. So you call it GAG, let's say, this augmented graph. I'll use this terminology all the time. Right. Now you can read off these separation statements here because this is an SCM. It implies its own conditional independencies. Because I always said whenever you have an SCM like this, it is semi-Markov with respect to the CPM. So deseparation statements hold, including all the latent variables. Therefore, any deseparation statement I read here will have an implication. Okay. So if I read any deseparation statement involving any other variable that's already taken care of. Right? I mean, suppose that T is equal to null and that's all. So in either of the distributions, I've already read deseparation statement. It's very simple. I just need to remove the edge into T and I read it. Or if T was null, I just take the original graph and I read it off. The only thing I have to tell you is, if I have some statement connecting PT and P, for example, what do these new deseparation statements involving F imply? Okay, that's the only thing I have to say, right? Now, let's consider the deseparation statement. Ft is actually independent of some y given x. Let's just consider this statement. And more importantly, x does not intersect t. So x intersection t is not very important. Okay. All this says is the mutual. So if this is true in the joint distribution where this is binarized, right? The mutual information between ft and y given x is equal to 0. Right? If this is true, this is also true. Okay, because I'm combining the data. So all I'm saying is, you give me data. I add one more column called F, and I say this is idle, this is interventional, and you just do a shuffle of all of this, and I create a joint distribution. Right? Now, this SCM gives rise to this data. And this deseparation holds, which means I can write this stuff with the ft being this indicator function. Clear? Okay. This simply implies by deseparation theorem. It's always true for any graphical model. So no faithfulness, no assumptions are needed. Right? This implies that probability of y given x, comma, ft is equal to idle is actually same as probability of y given x, comma, ft is equal to intervention. What does this mean? by just definition, this means that P of y given x is nothing but P of y given x comma do t. So I'm taking a conditional distribution in a new interventional distribution. I'm saying this is exactly equal to the observational distribution if this mutual information is 0 on this augmented data, which is implied by a d-separation statement. Okay. So the second rule, there's a more general version. I'm just trying to figure out how should I state it. Yes. So before, go ahead.
So I have a question. This is not necessarily true, but you're saying if this is true, this is.
No, I'm saying is this is true. This is a d-separation statement in the augmented graph. If this is true, this is true. That's all I've worked out. And the only link is d-separation theorem and the augmented definition of the SCM. So it's like an intervention can be thought of as affecting the functional relationship. That's all I'm saying. I'm not saying anything complicated. But the indicator that affects the function is like a parent node, and it depends on nothing else. Unless you saw the data and intervene, that's a different matter. But usually an intervention is forced. So if an intervention is randomized or it's a forced intervention on all the population, then FT has no parents, but it affects some other children. So for all the children it affects, you just put an arrow. It's a very simple device, nothing complicated here. But a d-separation involving F implies this distribution. Yes.
Sorry, but you have stated it as an implication, but this is always true, right? The first one.
This is not true. I mean, if you can measure, I mean, if you found that FT and Y are d-separated given X, then this is true. I mean, this is not true always.
If y belongs to t,
Yeah, that's the trivial case.
but if it is a descendant of t also.
Because FT goes to, so for example, I could have a graph like this, right? So if there is FT, you have T and then you have Y, but then there's something giving X. If you condition on X, nothing happens. Still FT is talking to Y, right? So in this case, this is not true.
One thing we put it into it, we want to understand when is a conditional observation distribution remains
Unchanged under another intervention. Exactly.
So what you do is construct this graph.
Yeah, but for that pair alone.
For
every pair, you need to construct this graph. This is a proof technique. This is a proof, actually, this is a full proof. But this is what is happening in the full proof. You construct an implicit SCM, and then you create the FT depending on what you want to contrast. Okay, the contrasting thing should have whatever interventional set that matters. Okay. Okay, now I'm going to generalize it a little bit.
Can't you do like, so it's kind of like saying you contract all of T into a meta node and test for these.
No, it's not contracting at all. It is having a parent that talks to all of them simultaneously. But it has no parents. You're just introducing more edges into the system.
Constructing a new graph, testing out d-separation.
D-separation, but you see, right, there's nothing I'm doing here. If you give me G, I'm just adding a bunch of arrows. I'm asking some new set of D-separation. If that holds, something remarkable is implied.
This statement is not trivial, but the top statement you give me, you need to check.
Yes.
Yeah.
Given G. And all that links is D-separation here. There's nothing else that has happened. Okay. So very remarkable device.
The first box does it have a structural understanding in terms of T itself? Though it's actually algorithmically very easy.
Yeah. So Phil Davitt, there's a lot of stuff he has written about this augmented graph formulation. So he tries to say that, I mean, that's his conclusion. There is again some disagreement between Pearl and him. I'm not going to get into it, but his main point is that if for some reason you're not allowing me to manipulate some set of variables ever, right? He says for every set of variables I can actually manipulate, draw an F node to that subset. right? And then use this mechanism to actually go through these interventional relationships. And whatever you can conclude from that, that's all you can conclude. Okay, that's a statement. That's a slightly reduced version of Pearlian causality, because Pearlian causality tries to do an intervention on almost anything. I mean, everything is free game, right? You give me a subset, just tell me X, okay, I can intervene. I mean intuitively, right? And you go through that. So what he says is that, okay, I want to avoid that. I want to say that certain things cannot be read from the graph. These augmented versions can do that. Because if there's a subset that you can't intervene on simultaneously, for whatever reason, there is no F node over there. So any proof that goes with, because whenever you add edges, right, you are creating new deseparation statements, right? They're very powerful. So the question is whether you want to have them or you don't want to have them. So what he's saying is that for every node that is not manipulable, you don't have these F nodes. That means it will result in only some bunch of deseparation statements. Only those things you can use to basically, churn your Pearlian theory. So they say, I mean, and he has a lot more things to say. And this node F node, it's called the augmentation. I mean, there are many names for this node. I just call it an F node. And this node is not a random variable. It is not observed in the real world. I am creating it. Okay. And deseparation is very valid, because I can always draw any edge into the graph, create a new graph and read something. But reading this implies this immediately by this operation. But if you want to go through this operation, you are assuming manipulability. You are assuming that physically I can do this, right? So there is some philosophical disagreement saying that you can directly define causality from this picture. You don't need to go to CBNs and then come from here. Don't define any truncated factorization. This is the definition of a causal model. Well, I mean, if you are very interested in such things, then yes. So there is some story behind this too. That's a good question, because this actually tells you the core idea behind just generalizing deseparation to intervention. That's all there is to it. But there is a more important thing that is being said, which is, in order for me to go from a combinatorial thing to a thing, yeah, deseparation theorem is important. But before I do that, I have to make sure that this is a random variable. But in order to make that as a random variable, I can't just go and intervene on anything. If it's not manipulable, I don't know what it even means. So some people say that this is a more general version of capturing manipulability, right? And Phil David has a lot of papers on this. You can go and read them. I don't know exactly what the final conclusion is, but I think there's some disagreement between Pearl and him, saying that you are essentially saying the same thing, and he says no, it's not. So yeah, okay. So but it matters for the uniqueness problem. If you forbade me from using some F nodes,
It's like asking the same problem under additional constraints.
Additional constraints. Okay, these F nodes are not available to you. Then what will you do? I can't do it. I mean, if that chain is required, you need to find an alternate chain. So it's like saying I have some bunch of production rules. I just delete some of the production rules. I have only remaining some of them. The question is, can you reach the observational data? Maybe you can't reach. So the open question is, what is the most general characterization? Most general characterization. If I can't intervene on blah, 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 and blah, I give you forbidden sets of interventions. Then how do you answer the uniqueness?
The computational version of that has been solved. Like I give you blah, blah, blah. You cannot intervene on blah, blah, blah.
Nobody knows what the uniqueness answer is. There is no characterization as far as I know.
Characterization is not there, but is there
I mean, if I don't even know when it is unique, when it is not unique, then what is the point of computation? So if people are interested in attacking the problem of manipulability, which is one of the criticisms, let's say, of Pearlian theories, because they say that, okay, you can get all this uniqueness, you can get all these results only if you can go from here to here. And in order to go from here to here, you're assuming you can manipulate something like this in the real world, which I'm not very comfortable with. Which means you are basically forbidding this F node, right? I can't use this, which means I can't test this Ft and Y and given X. Maybe some other T is possible, right? So if I give you a forbidden set, how would the theory generalize? Do you need something more? We have no idea. Or at least I'm not aware of it. Maybe some people are.
okay, so you were interested in knowing uniqueness with respect to T.
Correct.
And you assume here T is manipulable or not.
All T's are manipulable.
Answering this one, you didn't need all two, right?
No. I'm just merely stating if this is manipulable, this is true. If this is holds, this is always true.
Right.
But in the system, everything is manipulable. In order for the uniqueness theorem, I'm going to prove. I mean, the uniqueness theorem that exists doesn't. So if I,
you didn't need.
I don't need anything because I'm only going between these two distributions. Now I have to go through a chain and I might go through all possible manipulable sets. So the interesting question is if I ignore certain kinds of manipulable sets and I give you G, what can you do? Is the uniqueness holding? Is do calculus alone enough? Interesting question. Okay, but it's an open problem. you can try to solve it if you're interested.
Like, I can use this completely analytically. I mean,
No, but you are really talking about a true. I mean, see, when I mean intervention, I really mean a real world intervention. Yeah. Otherwise, why would I be talking about it?
but by that you mean that the right hand side exists.
Right hand side exists and it is manipulable in the way you claimed it is manipulable.
Okay.
Right? But I don't know. Maybe, I mean, what does it mean to say, I'm going to pinch your kidney and stop your 2 R's? Can you do that? I don't think so. You can do it, for example. That's what people do.
Or intervene on a G.
Intervene on a G. But what Paul will say is there is a G, but it is semantically possible. Maybe you can't do it, but why can't I go through that? So there's a philosophical discussion as to whether you can even go through this. That is left to, you see the problem, right? So the thing is, there's a constructive proof and they are saying this chain says something epistemic in the world for some people. I mean, you are saying it's a functional thing, so why do I care? Because there's an actual function. I'm not disturbing the actual function, I'm just augmenting it. So why do I care about that? But then what people will say is, no, but you are actually talking about a real intervention where T is supposed to T. There's nothing like that in the real world. Right? I mean, it depends on what status. See, the thing about causality that most people, it's not a mathematical axiomatization. Every time there's an implication, yes, whatever you can prove mathematically, you can prove, but there is an epistemic analog. Because the moment you talk about causality and intervention, you're really talking about real world intervention. Like I'm going to force that variable to T. If it's not possible, then what do you mean by this? Some people have a philosophical problem. Right? Epistemically, till here, everything is fine. But then what is this? What does it mean? Like, would the real world ever work like this? For that T? I don't know. Okay. Yes.
So a couple of questions. First, is there any parallel with respect to instrumental variables? In the PO world, you added some subset where you can intervene.
Yeah, good question. In instrumental case, this will not be true. But still you can say something under some parametric assumption. That's the instrumental variable. For linear alone, you can say something more concrete. So it's a special case. It's true, it acts like an instrument, correct. But in the instrumental case, if you think about it, the conditional independent statement you're looking for is not true. Okay, so it's a different thing.
And second, if there existed, if P overlapped with X.
Coming to that, we'll come to. That's the third rule. Okay, so now let me set a slightly more general theorem. I initially said this G could already be manipulated, meaning the left-hand side is already an interventional distribution. You're just comparing it with an additional intervention, right? So I'm just going to generalize. I'm not going to prove that here. It's just complicated. So the second, so this is called the do rule. At least one of my collaborators calls it the do rule because you just remove the do. There's a do C rule. So the do rule says that T of X given Y comma do T. Okay, I apologize. Y given X do T is equal to W actually equal to P of Y given X comma do W. If T is independent of Y given X, I mean B separated in GW bar. So on both sides, what is common? You always intervened on G do W. So remove the edges. Creates a new graph. With respect to that, there are two interventional distributions. One with do T and the other without that. This rule applies, and this deseparation statement must be tested in the manipulator. The general. But you only have to create an F node for the difference. That's the key. So both must exist. That's what some philosophers say. Okay, so whether you want to assign the epistemic, whether you want to assign an epistemic value to this equation or not is the philosophical choice. Mathematically, there's nothing I can say about it. At least my personal opinion. I don't know. Phil David might have other arguments. But,
Okay. Advertising application.
yes, there's one more rule, but it's 6 o'clock, so maybe I'll call it quits and then, or let me just state the rule, right? Okay, I'll state the rule.
Karthi says just to get the bigger picture, you have these three rules. And
You keep recursively applying to every query.
Yeah.
If you end up only with, so you see, right, this rule is very important because it removes 1, 2.
Yeah.
So if I keep removing all 2, then eventually end up only with observational distribution and then identify. Right, but there's one more rule. Very important.
sufficiency.
No, there's one more rule.
No, like the
Yeah, yeah, that's the proof in 2006. Yeah, that's a very remarkable, like that's a pivot element. It says I don't need to know anything about your functional mechanisms. Just give me G. That's it. I just apply these rules. If it ever gives rise to the observational distribution, it's uniquely identifiable over all models. Otherwise, it's not. 2006. Yes. Sufficient conditions are ones below before.
So these three rules are complete.
Complete and sound. If you can get there, it means the interventional distribution is reducible. And it's also complete that if you cannot get there, then nothing else can get.
It doesn't depend on faithfulness.
Nothing. That's a beautiful.
Because faithfulness is immediate, right? If this, no?
Why?
Because all
I haven't told you what the construction is here.
no, I mean all of these ifs are all if and only if.
Yes, true.
If it is faithful.
Yeah, but you will only use the forward direction always. Because I start from G, I'll only use the forward direction. I'll get the left hand side. Then I want to say it's equal to some right hand side. I'll again use only the forward direction. I'll keep going like this. If it stops, it's definite. So soundness doesn't need faithfulness.
Yeah.
That's very clear. Right? The completeness, we'll see. But it might be that the counter examples are faithful examples. It might be true, but the theorem itself does not depend on faith. You are not assuming anything else apart from the fact that there is. So that's a beautiful thing about it. Okay. So the third rule.
and completely structured.
Yeah, just completely combinatorial. Completely combinatorial. But just adding a bunch of arrows into the into it. And we'll show the exact same logic will be used in causal discovery. Basically, the intuition is that in causal discovery, the more non-trivial thing is the colliders. Once you get the skeleton, then you get the colliders. Imagine if you intervene, you're just adding more colliders into the system. Because you're creating nodes with no other parent. So it has to be unshielded. If it ever forms a collider with anything else, it has to be unshielded. So you're creating more colliders, which means more discoverable. So then you ask your question, how many colliders must be created before I can just figure out the orientation of everything in the graph? That's another way of thinking. So that's a paper by Caroline Wooler's group in 2018, where they formally showed that the same augmented thing can be used to define a Markov equivalence over interventional distributions. And there are generalizations of that, some minor, like we did one with semi-Markovian models that was only for Markovian. Okay. So last thing, do see, I think the time's up, so finish this. So I'll state the thing. I probably won't prove it. So what you do is this overlap thing that he was asking. So y given x comma root t comma w. See, it's better if all of them are disjoint. Okay, that's the easiest way to think about it. P of y given x comma t given w. Why is it called do C? There is a do here, but you're conditioning on T. So it's doing and then you're seeing. So you take a table, you see only T belonging to T and you take them out, that is seeing. Doing is you actually intervene and set that value to T. So that's doing. So this is called the do C rule. Okay. And it is very easy to check if Ft is independent of Y given X, comma T. So, okay, so why is that D-separate? T is I'm conditioning on the T on which the arrow is going into. So basically what I'm trying to do is I'm cutting off all the forward arrows. I'm only going behind T. I'm trying to check if we can still reach Y given X. If so, then the interventional distribution is equal to the conditional distribution. That's the intuition. So this actually captures the intuition of the backdoor form. We are saying no backdoor. That's what the do C basically says, right? So intuitively, we have Y. So by the way, for it to have a non-trivial effect on Y, I mean, Y must be a descendant of T. Otherwise, it's zero anyway, right? So you have T here, and let's say there's something going to Y. Let's say there's a path. Now, what we are saying is you already there's some W for which you've already done surgery, and you are in this graph. This is already GW bar, right? Now you are at T, and I have an F node to this. This is what we are testing, right? This is the difference between these two things. You are intervening here. You are not intervening. So that's why you add an FT here. Okay. Now what you're saying is that I'm conditioning on T. So how will F ever talk to Y? It will talk to Y only if there is a backdoor path like this. Because this guy cannot talk to anything else except T. So this can go up only if there was a path of this form with an arrow into T. Okay. And that's called a backdoor path.
Arrow into Y also.
Yeah, because otherwise they'll create a cycle. So arrow into Y also. But it can be left unspecified because this could be 0, then you can have an arrow like this. Okay. Right. Just giving an intuition when this is there, then yes, arrow has to be into Y. But usually it is specified as an arrow into T.
Yes, there can be colliders, there can be good things.
Right.
It doesn't mean a step.
Yeah.
Because you are conditioning on X.
Yes. So I'm conditioning on X, and still it has to be D. If it is D separate, basically if it is, I'm saying there's no such path because of the D separation. Then what I'm saying is interventional distribution is the same as the conditions. Right.
Ideally, if Y is all descendants of T, then interventional is equal to conditional. Right? If Y is all descendant of T.
No, not necessarily. This is the classic case, right? Like, yeah, Y is a descendant of T. Yeah, here conditional is not equal to it. Why? Because this is hidden by this. So this is the double arrow. So you do FT here. Now FT cannot talk to Y. That's great. But the problem is conditioned on T, FT can talk to Y. Okay, so interventional is not equal to conditional.
When you do this again, like my current understanding is much more for this moralization of ancestors. You will add edges out of FT when you are
Correct.
like,
More or less.
moralizing.
I mean, I generally think in terms of the original D-separation itself, because that's only computational help. This is much easier because I can track colliders very explicitly in my mind. That's really all you want to avoid, actually.
But yeah, if there is a collider, you will add an edge.
Yes.
Moralization.
And then you will go through that part.
Yeah.
Yes. Right. Yes.
Just to clarify, when you say no backdoor path, this corresponds to a backdoor.
Yes, this corresponds to a backdoor path. Therefore, this was not true.
Sorry, I mean the graph above, not.
Yeah, I'm saying this condition means this should not be. No such thing should be there.
So all paths to G, sorry, all paths to Y,
Y.
from T have to go out.
Yeah, how to go backdoor from T. That's what it implies in GW bar. If that happens, this distribution, this is always true. Okay, this trait implies the backdoor criterion, which will come to the next lecture. And some combination of these two will give you front door criterion, which is one of the very important implications of Pearlian theory. Because when I started the first class, you remember I told you the features are pre-treatment. So in PO, they always work with pre-treatment, most of the cases, right? So one important consequence is that the front door criterion, which says that even if you didn't know anything pre-treatment, and if there are certain types of graphs, if you know mediators, I can still use the mediators to actually estimate defect. So that is something that's a consequence of these two rules that you cannot easily derive from any other, as far as I know, any other. Okay. And then we'll go into Tian and Pearl's slightly more general sufficient condition. We'll give you more intuition about the backdoor, front door, maybe one more on Spitzer and Van der Waals result on how the backdoor looks, sort of. But I might only state the result. Then potentially I'll try to prove the Spitzer Pearl's thing. If possible, we'll see because it's a very complicated tool. So yeah.
This is an if condition and not if and only.
Yes. So everything is in one direction.
So for example, even if there is a backdoor path, it could be possible that there is.
Yeah, it could, but you can't conclude. So you will not use it.
Yeah.
And it will not hold in all models. That's the key.
There is a backdoor path, they will be deconnected, but they might be.
That's what it is.
And why it could be useless.
But if I move the model slightly, it will become dependent because of the faithfulness. So uniqueness will certainly not. At least this pair will not work. So these are basically the three production rules. And there's a theorem that says that all these three is what's required to solve the image.
How do you find this chain?
We will go that. So we need to develop more intuition. There's something called C components. We'll have C components coming.
Polydiag.
I don't know. I have to check. I don't think it's
Constructive.
It's constructive. It just goes enumerates over all subsets and tries to find something. So it's an enumerative algorithm, so it is constructive. But we'll not see that algorithm. We'll see the sufficient condition first, because that already gives you a lot of intuition. But the actual idea algorithm is very complicated. But I might do that.
In Markovian case, there is no chain.
There's nothing. I mean, there's nothing. I mean, you already know that explicitly, right? Like factorization.
From the first condition itself.
Yeah, it.
So even if certain things are not.
See, the thing is, all these things are still true. Only that there are no bidirected edges. So it'll all be very trivial things that you will be saying, which you don't require any complicated. Will always be unique. You can prove it yourself. There are no bidirected edges. You want to say that anything can be reduced to P of y given x. That's an exercise. But you don't need all of that way. You can just directly use the truncated. I mean, I have the explicit distribution with me, right? So why do I care?
They unobserved as sort of moved. They just random.
Yeah.
They're not doing anything. There is here unobserved like us.
Doing some complicated stuff. So this is the basic central piece. Sorry.
Here it is the fact that you're a function of your parents plus some noise.
So switch it off around.
So that type makes it very sort of